Hello everyone, welcome back to the channel. In this video, I am going to discuss electromagnetic induction. I will start with the Faraday's laws, followed by the concept of self and mutual inductance. In addition to this, I will also discuss the coefficient of coupling and dot convention in the coupled circuit. So let's start one by one. The first one is we need to understand that what is electromagnetic induction. So Faraday's had conducted his experiments and concluded that a current is generated in a coil as the lines of force bearing through the conductor are changed. The current which is generated is known as induced current, and the corresponding EMF that gives rise to the induced current is known as induced EMF. And this phenomenon of generating current in a closed circuit by changing the magnetic field through that circuit is known as electromagnetic induction. And the operation of all electrical equipment such as motors, generators, transformers is mainly based on the laws which are formed by the experiments conducted for electromagnetic induction, and these laws are known as Faraday's laws. So Faraday has given two laws, Faraday's first law and Faraday's second law. Faraday's first law states that whenever the magnetic flux associated with a closed circuit is changed, or we can say a cuts the magnetic flux, an EMF is induced in the circuit which results in an induced current. So basically, we say that there is an induced EMF whenever there is flux cut by the conductor. This is as per Faraday's first law. And Faraday's second law states that the magnitude of induced EMF generated in a coil is directly proportional to rate of change of that magnetic flux. And according to Faraday's second law, we get the value of induced EMF as minus n d phi by dt, where n is the number of turns on the coil and flux is given by phi, or phi is the flux, and this negative sign is according to Lenz's law, which states that the response opposes its cause. Now in this case, the response is induced EMF and cause is rate of change of current. So as per Lenz's law, the direction of induced EMF is always such that it sets up a current opposing the change in of the flux. So that's why we have a negative sign over here. Now when we have an induced EMF because of change of the flux, we have two different types of induced EMFs in the circuits. One is dynamically induced EMF. Dynamically induced EMF is the EMF which is induced when the conductor is moving. So that's why the name is dynamically induced EMF. And second one is statically induced EMF. Now statically induced EMF is conductor is remaining stationary, or we can say the coil is remaining stationary, but the flux linking with it, that is going under the change, and that is resulting in an induced EMF. So this statically induced EMF is of two types: self-induced EMF and mutually induced EMF. From self-induced EMF, we will have the concept of self-inductance, and from mutually induced EMF, we will have the concept of mutual inductance. Now, taking them one by one, we need to understand the self-inductance and mutual inductance. Self-induced EMF is the EMF which is induced in a coil. Let's say we have a coil with n number of turns. When current I is flowing through this coil, this leads to production of flux phi, and that flux phi links with this coil. When this flux phi links with this coil, then there is an induced EMF in this coil as per Faraday's law, which is given as minus n d phi by dt. Now, since this is an induced EMF because of flux linking with the same coil, and that flux is produced by the current which is flowing in the same coil only. So that's why it is known as self-induced EMF. Now this phi is proportional to current I. So we can write that phi is equals to C into I, where C is constant, or this constant can be written as phi by I. Now in EMF equation, if we use the value of phi as C into I, since C is constant, it will come out of the integration minus nc di by dt. Also, we have written that C is equals to phi upon I, so minus n phi I into di by dt. This n phi upon I is written as L, which is known as coefficient of self-inductance, or simply self-inductance. L is self-inductance, or known as coefficient of self-inductance. Its units are Henry. So we can say the coefficient of self-inductance L of the circuit is defined as magnetic flux linked with the coil when a unit current flows through it. So L is equal to n phi by I. N is the number of turns of the same coil, phi is the flux produced because of the flow of current I through the same coil. Since everything is associated with the same coil, that's why it's known as self inductance. Then we have mutually induced EMF. For mutually induced EMF, we need two coils. Let's say this is the first coil, which is having number of turns N1, and the second coil is having number of turns N2. Current I1 is flowing in the first coil, and because of that, flux phi 1 is produced. Flux phi 1 is produced. Now, this flux phi 1 is linking with the second coil as well. Now, it's not necessary that it's always 100%. It may be some percentage of the flux produced in the second coil. So, let's denote the flux linking with the second coil because of flow of current I1, as phi 21. So it is given as phi k into I1, where k is the friction by which the flux linking with the second coil because of flow of current in first coil. So basically the maximum value of k can be 1. When k is 1, it means there is 100% flux linkage. Minimum value is 0, means there is no flux linkage with the second coil because of flow of current in first coil. It lies between 0 and 1. This is known as coefficient of coupling that we need to find out. Also, phi 1 is proportional to I1. So we can say phi 1 is equals to C1 I1. Or C1 is equal to phi 1 upon I1. Now, as per Faraday's law, the induced EMF in second coil is equal to minus N2 into the flux linking with the second coil. Now that is phi 21 minus d phi 21 by dt minus N2. Now d phi 21 is equals to k into phi 1. K is constant, it will come out of differentiation d phi 1 by dt minus N2 k d phi 2, sorry, phi 1 can be written as C1 I1. So C1 will also come out of the differentiation since it's constant. So this will become di1 by dt minus N2k. Now C1 can be written as phi 1 upon I1 into di1 by dt. K into phi 1 is phi 21. So this is equal to minus m di1 by dt, where m is known as coefficient of mutual inductance or simply mutual inductance, and m is equal to N2 phi 21 upon I1. Now N2 is the number of turns of the second coil, I1 is the current flowing in the first coil, and phi 21 is the flux linking with the second coil because of flow of current I1. Similarly, there is possibility that we have current flowing in the second coil, and because of that there is flux produced in the second coil phi 2. Phi 12 will be equal to k into phi 2. Now this phi 12 is the flux linking with the first coil because of flow of current in the second coil. Phi 12 is flux linking with coil 1 due to flow of I2. So similarly, we can find out the mutually induced EMF in the first coil as well. So it's better that we write this one as mutually induced EMF in first coil. Similarly, we can write the mutually induced EMF in the second coil. So that in that case, EM2 will be equal to minus M di2 by dt, and M will be equal to N1 phi 12 upon I2. So this can be written on the similar grounds as we have written EM1. So mutual inductance Since it's associated with the two coils, it can be given by this expression as well. So coming to this first expression, M is equals to N2 phi 1 upon I1. We had already written that this phi 1 is equals to K into phi 1 into I1. So this is our first equation. Second equation is from here, M is equals to N1 phi 2 upon I2. Phi 2 is K into phi 2 upon I2. This is our second equation. Now when we multiply first equation by second, multiply first by second, then we have M square is equals to N1 into K square phi 1 phi 2 upon I1 I2. Now if we separate the terms, N1 phi 1 upon I1, N2 phi 2 upon I2 into K square. This N1 phi 1 upon I1 is known as self-inductance of first coil. N2 phi 2 upon I2 is the self-inductance of second coil. K square M square. So K, which is coefficient of coupling, is given by M upon root L1 L2. So this K is coefficient of coupling. So this coefficient of coupling actually depends upon the mutual inductance and the self-inductance of these coils. Now before moving on to the calculation of equivalent inductance, we need to discuss the dot convention, which is used in mutually coupled circuits. Now, dot convention is used for mutually coupled circuit. We have seen that in the coil we have mutually induced EMF as well as we have self-induced EMF. It's better to write this one as ES. Self-induced EMF, mutually induced EMF. Now whether the self-induced EMF and mutually induced EMF, they are in same direction or they are in opposite direction, that is decided according to the dot convention. So dot convention is used for mutually coupled circuits. Let's say we have two coils or two inductances which are mutually coupled, and a dot is marked over here, which indicates that they have mutual coupling between these terminals. Now the current in the first coil is in I1, current in second coil is I2. So if we have to write the induced EMF in first coil as well as in second coil, then E1 will have two components. One is self-induced EMF and second one is mutually induced EMF. Similarly, E2 will have again two components, self-induced EMF and mutually induced EMF. As per dot convention, we will see whether the mutually induced EMF is in same direction with self-induced EMF or it's opposing the self-induced EMF. We can write the self-induced EMF for first coil as L1 dA1 by dt, then my negative sign overall. Then mutually induced EMF. Now this mutually induced EMF will be in same direction with the self-induced EMF if both the currents I1 and I2, they are entering the dotted terminal of the mutually coupled circuit. Now this I1 is entering the dotted terminal, I2 is also entering the dotted terminal. So mutual inductance will have the same direction. So it will be equal to minus M di2 by dt. Or we can say L1 di1 by dt plus M di2 by dt. Now this negative sign, which is over here as well as over here, this is as per Lenz's law. Otherwise, the self-induced EMF and mutually induced EMF, they have same direction. Similarly, for second coil, the self-induced EMF is L2 di2 by dt. Mutually induced EMF is M di1 by dt. And we have a negative sign as per Lenz's law. But the self-induced EMF and mutually induced EMF, they are in same direction, since I1 and I2 both are entering the dotted node. Now we can have the same expression of E1 and E2 if currents are leaving the dotted node. Or we can say the direction of the dotted nodes are at same place over here, but current's direction is now reversed. I1 is leaving the dotted node, I2 is also leaving the dotted node. So in this case, we will have the same expression of induced EMFs. We might have the case that one of the current is entering the dotted node and second one is leaving the dotted node. So I1 is entering and I2 is leaving the dotted node. In this case, the induced EMF in first coil, which is sum of its self-induced EMF and mutually induced EMF in coil 1, that will be equal to minus L1 di1 by dt. Then we have the value of this mutually induced EMF as minus M di2 by dt. This negative sign is as per Lenz's law, but since the current I2 is leaving the dotted node, I1 is entering the dotted node, so both the induced EMFs, they are in opposite direction. So this sign will be replaced by a negative sign. They are opposite in nature. So the self-induced EMF is minus L di1 by dt, and then we have plus M di2 by dt. Now this expression is equally valid if the current I2 is entering and I1 is leaving. Then again this expression is applicable. Since one current is entering and second one is leaving, similarly E2, that will be equal to self-induced EMF plus mutually induced EMF. Self-induced EMF and mutually induced EMF, they are opposite in nature. So L2 di2 by dt plus M di1 by dt. So minus sign is associated with the both the induced EMF because of Lenz's law, and second negative sign is there with mutually induced EMF since it is opposing the self-induced EMF. So this dot convention is very important to calculate the equivalent inductance when the mutually coupled inductances are connected in series as well as in parallel. In next video, I will find out the expressions of equivalent inductance for mutually coupled circuit and followed by some numerical problems. Thanks for watching the video.